Hello, everyone. In this talk, I'll present CoVisor, a compositional hypervisor that allows network admins to compose multiple controllers on the same network. SDN is a major trend in networking. It provides centralized control of networks with open APIs. We can run management applications on the controller to manage our network. However, network management involves a wide variety of tasks, like microlearner, firewall, gateway, monitor, and IP router. It is very hard to develop and maintain a monolithic application for all these tasks. Therefore, a more desirable way is to develop multiple applications independently for these tasks. Frenetic is a recent solution along this way. It provides a domain-specific language and a runtime system. Applications written in Frenetic can be composed with composition operators and run on top of the Frenetic controller. But to get these benefits, it requires both the network admins and the companies to adopt the Frenetic language and runtime system. However, in reality, the best-of-breed applications are usually developed by different parties using different programming languages and run on top of different controllers. For example, the best microlearner may be provided by company A and runs on top of POX, and the best firewall may be provided by company B and runs on top of RAU. To fully realize the vision of SDN, we should be able to mix and match these third-party controllers. Frenetic is not able to do this. Network hypervisors are a possible solution to run multiple controllers on the same network. However, current network hypervisors like FlowVisor and OpenVertex only support slicing. With slicing, each controller works on a disjoint slice of the traffic. For example, if we have a firewall controller and a router controller, then the traffic is either processed by the firewall or the router. This can be useful for scenarios like multi-tenancy, where each tenant only manages his own traffic. But in our scenario, we want multiple controllers to collaboratively work on the same traffic. For example, we would like the traffic to be first filtered by the firewall, then be routed by the router. So slicing cannot fulfill our need. To solve this problem, we propose CoVisor, a compositional hypervisor for software-defined networks. CoVisor provides a clean interface to compose multiple controllers on the same network. The interface includes two parts. In the first part, we provide several composition operators to compose multiple controllers. And the second part provides constraints on individual controllers. It allows network admins to restrict what each controller can see by providing a virtual topology to each controller, and restrict what each controller can do by impose fine-grained access control to each controller. Now let's go into more details. We provide three operators to compose multiple controllers. The first operator is parallel operator, which allows two controllers to process packets in parallel. For example, in many times, we want to have a monitor controller to monitor our network and have a router controller to route packets at the same time. This can be very naturally expressed by a parallel composition of a monitor controller and a router controller. The second operator is the sequential operator, which allows two controllers to process packets one after another. For example, we can have a firewall controller to filter packets first, and then have a router controller to handle all the filtered packets. The third operator is override operator, which allows one controller to choose to act or defer the process to another controller. For example, when we do traffic engineering, we can have an elephant flow router to handle all the elephant flows. Then we have a default router to handle all the remaining traffic. We can also use multiple operators to compose more than 2 controllers. For example, we can have a firewall controller to filter packets first, then we have the monitor controller and the router controller to process packets in parallel. Composition is mainly about how to compose multiple controllers. For each controller, CoVisor also provides an interface to specify what they can see and what they can do. CoVisor provides 2 primitives to create virtual topologies. So each controller only sees a virtual topology instead of a physical topology. This limits the controller's visibility into the network and helps network admins to hide their physical infrastructure information and reuse controllers that have specific requirements on topologies. It also provides a new way to do composition. The first primitive is many-to-one, which virtualizes multiple physical switches into a single virtual switch. For example, we can simply expose a big virtual switch to a firewall controller because the firewall does not have to know the physical connectivity to filter the packets. The second primitive is one-to-many mapping, which virtualizes a single virtual switch into multiple, which virtualizes a single physical switch into multiple virtual switches. For example, the virtual switch S here connects an Ethernet island and the IP call. For the traffic inside the Ethernet island, the switch S acts as a MAC learner. And for the traffic inside the IP call, the switch S acts as the IP router. And for traffic between the Ethernet island and the IP call, switch S acts as a gateway. We can virtualize this switch S into 3 virtual switches, EG and I, and we can break its functionalities into 3 parts and have 1 controller to take care of each part. In addition to use virtual topologies for each controller, we also restrict what each controller can. We also provide an interface to restrict what each controller can do. This helps protect the network against buggy or possibly malicious third-party controllers. The restriction has 2 parts. The first part specifies the header fields and the match types a controller can use to match packets. For example, we can restrict a MAC learner to only do exact match on source MAC, destination MAC, and import. So the MAC learner would not be able to look into other header fields like IP address. The second part specifies the actions a controller can perform on the matched packets. For example, we can restrict a MAC learner to only forward or drop packets, so it would not be allowed to modify any header fields. This figure shows a high-level architecture of CoVisor. CoVisor is a transparent layer between the network and the controllers. It uses OpenFlow to speak to the switches and the controllers. To compose multiple controllers, CoVisor first uses the 2 primitives to virtualize the physical network into a virtual network. Then it exposes a part of the virtual network to each controller. And if a virtual switch is exposed to more than 1 controllers, we need to use compositional operators to specify how we want to compose multiple controllers on the virtual switch. Controllers send OpenFlow rules to the virtual switches to realize their network management tasks. The job of CoVisor is to compile flow rules received from controllers to flow rules for the physical network. The key challenge of CoVisor is to make this compilation process highly efficient. The compilation involves 2 steps. In the first step, since a virtual switch may receive flow rules from multiple controllers, CoVisor composes them into a single flow table for every virtual switch. Then in the second step, given the flow tables for each virtual switch, we compile the flow tables into flow tables for the physical network. Now let's go into more details of the compilation. The first step is to compile policy compositions. A policy is a list of rules where a rule has a priority, a match, and an action. For example, the monitor controller has 2 rows, and the first row has a priority 9. It matches on source IP, and its action is count. The goal for this compilation step is to compile policies from multiple controllers into a single policy. To do this, we need to iterate over all the rule pairs between the monitor policy and the router policy. Specifically, when we compose the first row in the monitor and the first row in the router, we generate a row which matches on both source IP and the destination IP. And its action is both count and forward, because parallel composition gives the illusion that packets are processed by these 2 controllers in parallel. After we iterate over all the rule pairs between the 2 policies, we can get the 4 rows in the composer policy. And we leave the priorities as question marks, which we will fill later. Controllers continuously update their policies in response to various network events, like a traffic matrix change or topology change. When CoVisor receives these rule updates, it has to recompile its policy and update the switches accordingly. For example, now we have a new rule which is inserted into the router policy. How would the CoVisor recompile the policy and update the switches? We want to minimize 2 kinds of overhead during this process. The first overhead is computation overhead, which is the computation it takes to recompile the new policy. And the second overhead is rule update overhead, which is the number of rule updates we need to update switches to the new policy. It turns out that the way we assign priorities is closely related to the efficiency of the compilation. First, let's take a look at a naive solution, which simply assigns priorities from the top to the bottom by a decrement of 1. So the first row gets a priority of 3, and the last row gets a priority of 0. Then when we insert a new row into the router policy, it has to recompute the entire policy from scratch, because it needs the relative location of the rows to determine the priority for each row. If we compare the old flow table and the new flow table, we can see that it incurs very high computation overhead because it has to recompute the entire flow table from scratch. It also incurs very high rule update overhead because although there are only 2 new rows, but 3 more rows change their priorities, so we have to update 5 rows in total. So to solve this problem, we observe that rule priorities form a very convenient algebra that allows us to incrementally compile policies and update switches. Specifically for the parallel composition, we add the priorities of the original rows together to get the priority for the composer rule. As in the example, we add the priority of the first row in monitor and the first row in router to get the priority for the composer rule, which is 16. With addition, we can calculate priorities for all the rows in the compose policy. Then when there is a new row inserted into the routing policy, we only need to compose this row with the rows in the monitor policy. This generates 2 new rows. Then if we compare the old policy and the new policy, we can see that it incurs very low computation overhead because we only need to compute the new rows. We do not have to compute the entire policy from scratch. Also, it incurs very low rule update overhead because it only adds 2 new rows. All the existing rows don't change. For sequential composition, we cannot not do addition because the 2 policies connected by the operator are not symmetric. We need to prioritize the first policy. Therefore, we concatenate the 2 priorities to calculate the priority for the composer rule. With the concatenation, the priorities in the composer policy form a lexicographic order. As in the example, we put the priority of the first row in the load balancer policy to the high bits, and the priority of the first row in the router policy into low bits. And this gives priority 25 to the composer rule. And with concatenation, we can calculate the priorities for all the rows in the composer policy. Finally, for the override composition, since the policy on the left has strictly higher priority, So we need to stack the priority space of the left policy above the priority space of the right policy. In summary, with this convenient algebra on the rule priorities, we can incrementally compile the policies and update the switches. Details for more explanations and proofs of the correctness of the algorithm can be found in the paper. After the composition, we generate flow tables for each virtual switch. So the second step of the compilation is to compile the flow tables in the virtual network into flow tables for the physical network. Since the many-to-one mapping has already been explored by many previous works, in this talk, I will mainly focus on one-to-many mapping. I will use an example to illustrate the one-to-many mapping compilation process. In this example, we have a physical switch S virtualized into 3 virtual switches, EG and I. We already have the flow tables in the virtual switches. For example, virtual switch E has 2 rows, E1 and E2. Now the problem is how do we compute the flow table for the physical switch S. To do this, we first inject a symbolic packet that covers the entire flow space from each ingress port of the virtual network. Then we follow the symbolic packet to go through the network. This gives us a symbolic tree rooted at the ingress port. Then for each branch of the symbolic tree, we do a sequential composition for the rows on the branch. For example, the first branch has only 1 row, E1, and the second branch has 3 rows, E2, G1, and I1. We sequentially compose the rows on each branch. This gives us 3 rows, S1, S2, and S3. Finally, before we install these 3 rows into the physical network, we need to augment the priorities. Because these different branches have different hops, we need to augment the priorities for the shorter branches to make sure that the resulted rows have correct orders. And this finishes the compilation from the physical topology into the physical topology. We have implemented a prototype of CoVisor, and the code is open source. You are welcome to visit our project website, covisor.cs.princeton.edu, to access to our code, the tutorial, and other materials. We have done evaluation on several user cases. In this talk, I will show the results of a parallel composition of a layer 2 monitor, which monitors packets based on source and the destination MAC address, and a layer 2 router, which forwards packets based on the destination MAC address. The first figure shows the compilation time of inserting 1 rule to the monitor policy. The y-axis shows the compilation time, and the x-axis shows the router policy size. We fix the monitor policy size into 1,000 rows. From the result, we can see that the Strawman solution that assigns priorities naively from top to the bottom by a decrement of 1 takes hundreds or even thousands of milliseconds to recompile the policy, because every time when it receives a rule update, it has to recompute the policy from scratch. In contrast, CoVisor only takes a few microseconds to recompile the policy, because it only has to consider the new rule. The second figure shows the rule update overhead. The y-axis is the number of flow modes it takes to update the physical switch to the new policy, and the x-axis is the router size. The router policy size. Again, the result shows that with the Strawman solution, it needed to send thousands of flow modes to update the switch, because many existing rules change their priorities. On the other hand, CoVisor only needs to insert the new rule, which incurs significantly less overhead. In conclusion, we present CoVisor, a compositional hypervisor for software-defined networks. It provides a clean interface to compose multiple controllers on the same network. And you are welcome to visit our project website to get more details. And currently, we are working with Unlab to integrate some features of CoVisor into ONOS. And that's all for my presentation, and I'd like to take questions.
questions?
Hi, I'm Edward Dremel from Cornell, and I wonder what the overhead comparison is between this approach and actually running frenetic. If you had your ideal world where each of these controllers was in frenetic, and you compare the time it takes to compose and run all the rules to when you're running each on a separate platform and using CoVisor.
So the overhead to running CoVisor is significantly lower than frenetic because our compilation uses a very convenient algebra on priorities, which significantly reduce the overhead when you do compilation and do the rule update.
So you say it's actually faster to compose multiple controllers here than it would be in frenetic?
Yep.
Interesting.
Grace from George Washington University. In practical paper, they already provide like virtual topology abstraction, like one-to-many mapping and many-to-one mapping. So I'm wondering, how does your virtual topology mechanism different from theirs?
Okay, so in here, for frenetic, the one-to-many mapping is reactive, which means for every packet, you have to send the packet into the controller to get the packet to be processed. Here, our solution is proactive, which means we get the rules from the controllers and compile into the flow tables for the physical network. So it's difference between reactive and proactive.
Okay, thank you.
Yeah, thank you.
Let's thank the speaker.